Hi, Larry Elterman here again, and today I'm going to talk about cycle stop valves. This is a piece of equipment that's supposed to go in your pressure tank system. When you have a water system that has a pressure tank and a pump, you're supposed to put this valve in, and it's supposed to help you in many ways. It's supposed to even out the pressure, reduce the number of cycles that the pump goes on and off, save you electricity, save you money, wear and tear on the pump, etc., etc. If you look at the advertising for this product, they make it out like there's no downside to this product and that it's the greatest thing since sliced bread. There's only one problem, and that problem is that this is actually a bad product. It really doesn't do any of the things they say it does. The information they give is very misleading, and I'm going to prove to you today why it's a bad product. So here's what I'm going to do today in this video. First, I'm going to give you a quick overview of what it is and how it works very quickly so that you know what I'm talking about. Then I'm going to tell you what they, and by they I mean the promoters of this product, say it does for you. I'm going to, from their point of view, I'm going to tell you all the things that they say it does for you. And then I'm going to show you how they promote this product tooth and nail with both misinformation and disinformation and pretty close to downright lies. And then I'm going to show you in more detail how it works and what exactly it does. And finally, I will explain why it is a bad product and why it does not do the things they say it does and why it will cost you money if you buy this product. Not only the cost of the product itself, but it will actually cost you money in other ways. And it is just not a good product, and I'm going to show you why. Okay, so this is a picture of a standard system, a simple standard system, which consists just of a well with a submersible pump in it. When water is needed, the pump pumps water up through this pipe. The pressure is monitored by this pressure switch, and the water comes to this T over here. And if people are using water, then the water goes through the T to the people that need it. And if the water is not being used or not being used quick enough, some of that water is diverted into the pressure tank. Because usually the pump is pumping water faster than people can use it. So the pressure builds up in the pressure tank until it reaches 50 psi, because this pressure switches from 30 to 50 psi, and then the pressure will shut off. So the pump tends to go on for a while, fill up the tank, and then go off for a while. And so now let's look what happens when we install a CSV valve. The CSV valve is installed at this point here. It replaces the normal T. And what it does is it's able to restrict the flow going through this valve. It creates a back pressure. It restricts the flow coming through here so that the pressure never goes over 40 pounds. You reset this CSV valve to 40 pounds, and as the pressure starts to build up, when it hits 40 pounds, it starts restricting the flow so that the pressure never builds up to 50 pounds, and as a result, the uh, the the pressure switch never turns off the pump, and the pump keeps on running, and the pressure stays at exactly 40 pounds. Finally, when nobody's using the water at all, everybody shuts off their water, what happens is this pump, this valve doesn't restrict the water 100%. It allows a little bit of water to go through, up to 1 gallon per minute. So what happens is after everybody turns off the water, slowly the pressure tank is refilled until it hits 50 psi, and then the pump finally shuts off. So why do they say this is such a great thing? Well, first they tell you, gee, don't you like constant pressure? If you have a regular system, your pressure is going to vary from 30 to 50. If you have a CSV valve, your pressure will stay exactly at 40. And that's really nice. You know, if you're in a shower or you're doing something, your pressure stays at exactly 40. And that's a good thing. And then they're also telling you that if you use something that's on for a long period of time, like a long shower or a sprinkler system, then what normally happens if you have a regular system is the pump cycles on and off as it fills the pressure tank, and then the pressure tank is emptied. It goes from 30 pounds psi to 50, and then it turns off, and then it goes down to 30 and turns on, and goes back up to 50 and turns off. But with a CSV valve, it stays at 40 pounds, and the pump never goes off until finally the water is finished being used, and then finally the pump will go off. And the CSV people tell you this is a great thing because when the pump goes on and off, this causes a lot of stress to the pump. And by saving you cycles, by not having the pump go on and off all the time, the pump will last way longer, they say, and this will save you a lot of money. So this is how they promote this product, telling you it's such a wonderful, great product. So there's this company called Cycle Stop Valves that makes and promotes these valves, and this is their logo right here, and you see their website over here, and there's this man who is constantly promoting these. I'm going to call him CSV Man. That will be my nickname for him. I don't know his real name, but I'm going to call him CSV Man. And you see him everywhere. When there's a video about a water tank system, he'll come on and with the comments, and he'll say, what you really need to solve your problem is a cycle stop valve. And he has a bunch of videos where he promotes these things ruthlessly and non-stop. I mean, tooth and nail, he will promote these things. And if anybody puts out a comment that's negative, he will refute that comment. Even if his refute is wrong, he'll just he'll swamp you in technical information and gobbledygook so that you don't really know what's right or wrong. And he'll try to convince you that if anybody says anything bad about this product, they're wrong. And this is the greatest product in the world, and that you better not criticize this product because this product is just fantastic. Okay, so I'm going to give you some examples of this. So here's an ad that I'm sure he had something to do with, and let me read this ad to you. It says, while cycle stop valves are in place around the world, Carrie Austin, maybe he's the cycle stop man, Carrie Austin, the inventor and owner of Cycle Stop Valves, headquartered in Texas, says there are still disbelievers that can't fathom the simplicity of a mechanical valve that can deliver constant water pressure with equal efficiency from small flows like a single garden hose to as much flow as the pump can deliver. The warning says, if it sounds too good to be true, it probably is. That comes to mind when you are promised overnight weight loss and gimmicks that make you rich. But sometimes an invention comes along that delivers what it promises so well that it really does seem too good to be true. Well, guess what, Cycle Stop Valve Man? You're only proving that the saying is true. It is too good to be true. And I'm going to show you why it's too good to be true. I'm going to show you why it's not so true. Okay. So he has a bunch of promotional videos. One of them is this promotional video that he has on YouTube. And it shows you how a cycle valve works. In fact, you can look at this video if you want a simulation of how the cycle stop valve works. And then he promotes and tells you why it's the greatest thing since sliced bread. And if you comment on this site, he will refute your comments. If it's a negative comment, he will refute your comments. Now I'm going to give you some examples. Okay, so after I posted one comment on his site explaining how that sometimes the cycle stop valve doesn't reduce cycles, but it actually increases cycles, and I said you should explain that, his answer is, I am not glossing over anything, as there is really no downside to the CSV. You just don't understand the principle. Well, there are downsides to the CSV, and you're wrong. I do understand the principle. I understand the principle perfectly. And in fact, I understand it so perfectly that I'm going to be able to refute everything you say. Okay, let's go on to another quote from this guy called Duval Doder. And he put this comment on this video, and it was a very long comment with great detail, and he explained in great detail why his product doesn't do what it's supposed to do, and how this product is actually going to cost you a lot of money. And then this was his answer to Duval Doder, if I'm pronouncing it right. Pump and motor manufacturers blacklisted the CSV as a disruptive product in 1994. That means the CSV works so well it would put pump and tank companies out of business. So they will do or say anything to keep you from trying one. I don't think you know as much as the engineers from Gould's or Grundfos or Pentair or Berkeley. They all know the CSV is the best thing for any pump system, which is why they want you to keep letting your pump cycle itself to death with your big 300-liter tank. Almost 30 years and 1 million CSV customers are not wrong. You are. Okay, so give me a break. It's like he's so sure the person is wrong, even though the person showed in great detail. He didn't show how the person was wrong. He just said you're wrong, and it's like a conspiracy theory. Everybody hates his product because it works so well. It works too well. And finally, here's another quote. When somebody explained why the CSV could in fact cause excess cycling rather than reduce the cycling, then he says, there is also no reason you can't use a CSV with a large pressure tank if you wanted. You would just be wasting money and space and not be getting the good, strong, constant pressure like you would with a CSV and a small tank. Well, this is kind of a weird argument. What somebody pointed out to him is that when you set up the configuration that he suggests, that in some cases the pump actually cycles on and off more often. And then his answer to that is, well, if you don't like that, buy a big tank. But if you buy a big tank, then the CSV doesn't deliver constant pressure. And in fact, the system acts just like a regular system with a big tank. So he's trying to have it both ways. If you tell him that it's cycling on and off too often, he says, get a big tank. And if you tell him with a big tank there's not constant pressure, then he says, get a small tank. So it doesn't make a whole lot of sense. Okay, I'm going to be doing some concrete scenarios, some concrete examples to prove how the CSV valve is actually a bad product and that the things that they say are not true. In order to do that, I have to make some assumptions about the pump size, the pressure that's being used, and the tank size. So I'm going to come up with these examples for our scenario. So for the pump size, I'm going to use a 3/4 horsepower pump. That's about 600 watts. It delivers a maximum pressure of 75 psi, and it has a maximum flow rate of 12 gallons per minute. For our pressure switch, our pressure, I'm going to have a cut-on pressure of 30 psi and a cut-off pressure of 50 psi. That means the pressure will vary between 30 and 50 psi. Now, we're going to have two different pressure tanks, one for the regular system, the standard system, and one for the CSV system, because the CSV system is supposed to have a small tank. Now the pressure tank for the regular system, we're going to use a 25-gallon bladder tank. This is a typical tank for a residential use. And when you have a 25-gallon bladder tank, the drawdown at a 30 to 50 range is 8 gallons. Okay, so a lot of people don't understand this. They think that if you have a 25-gallon tank, you're going to get 25 gallons of pressurized water. This is not true because the tank is always filled with a mixture of air and water. And if you have a 25-gallon tank operating at a 30 to 50 pressure range, you're going to get 8 gallons of drawdown. What this means is that when the pump finally goes off, there'll be 50 pounds of pressure in the tank, and then the pump will go off and you'll be drawing water from the tank until the pressure goes down to 30, and then the pump will go back on. And the amount of water you get from the time that the pressure is 50 to the time the pressure is 30 and the pump goes back on is called the drawdown. And with this size tank, you get an 8-gallon drawdown. Now for the CSV system, we're going to use a small tank as recommended. This is only going to be a 3-gallon tank. and the drawdown will be only 1 gallon. Now I want to point out a couple of things about these figures before I go on. These are very typical figures for residential use. These are not low end or high end. This is right in the middle. So this 3/4 horsepower pump is typical for residential use. A 30 to 50 pressure range is a common pressure range, and these tank sizes are also this tank size of 25 gallons is a typical tank size for residential use. Now you might want to write these figures down or print it out if you can, because I'll be coming back to these figures over and over again during the examples. Okay, what I'm going to do now is compare the performance of a non-CSV system, that is a normal system, to a CSV, that is a cycle stop valve system, in 4 different scenarios as follows. Scenario 1, using the water frequently for short periods of time. Example, washing hands, flushing toilet, etc. Scenario 2, using the water for a long time but with a low flow rate. Example of this is a long shower. Scenario 3, using the water for a long time with a faster flow rate that is still less than the pump's capacity. Example, running a sprinkler. So the pump is pushing the water fast out the sprinkler, but not as fast as it could. There's still some reserve capacity to the pump. Scenario 4, using the water for a long time with a flow rate that uses the full capacity of the pump. An example of this might be filling a swimming pool, and you have a large hose and you turn the water on full to fill the swimming pool. Okay, so here is scenario 1, frequent water use for short periods of time. This is, for example, you're cooking in the kitchen for an hour, you're washing your hands, rinsing a dish here and there, flushing the toilet, running the garbage disposal. Let's assume that we wash our hands 8 times, rinse a dish 8 times, flush the toilet twice, and use the garbage disposal twice. For simplicity, we will assume that each usage is 20 seconds at a flow rate of 3 gallons per minute, which uses 1 gallon for each usage. There is a total of 20 separate usages of the water that's turning on the water, 20 separate times. These are separate usages with a time interval between each use. So let's look at the math here. Now, I'm not going to go into the details of all the math. If you're interested or into this kind of stuff, you can check my math and make sure it's right, but I'll just sort of gloss over it quickly. In the first scenario, you're using the water 20 times, but you're drawing off a pressure tank, a large pressure tank with an 8-gallon drawdown. So you don't turn the pump on. The pump isn't turning on each time. And in fact, as it turns out, the pump will go on 3 times, and the total time will be for 2 minutes. But with a CSV system, every time you use water, the pump will go on, every single time. And when it refills the small tank that it has, it will refill it at a small rate, because the CSV valve will prevent the small tank from filling up at a quick rate. So that's the math of the CSV system. Please check it in detail if you want. Now let's look at the recap of the S1, the scenario 1 recap. So let's look at the number of cycles and the number of times the pump turns on. For the standard system, it will turn on 3 times. But for the CSV system, it will turn on 30 times. So Cycle Valve Man, CSV Man, is trying to tell you that you'll save cycles. And you will in some cases, like when you're using long periods of water. But when you're using short periods of time, you don't save cycles, you waste many, many cycles. And let's look at the runtime in our scenario. The runtime for the standard system of the pump is only 2 minutes. But for the CSV system, it's 13.3 minutes. So you're using 6.65 times more electricity. And note also that the CSV is supposed to provide constant pressure, and it does if you're using it for a long period of time. But when you're using it for a short period of time, you actually get wild fluctuations, because you turn on the water, and first you're starting at the high of 50 pounds, but because you have a small tank, it quickly goes down to 30 pounds. Then the pump goes on, and it shoots back up to 40 pounds, and finally it will stabilize it at 40 pounds of pressure. So you certainly don't get a constant pressure in this particular scenario. Okay, so now let's look at scenario 2, long usage with a low flow rate. An example of this is a 20-minute shower, and a typical shower has a flow rate of 2 gallons per minute. In this case, a total of 40 gallons will be used. So I'm not going to go into the details of all the math, but basically with a standard system, you'll be drawing off the pressure tank, and the system will go on 5 times. Each time it goes on, it will go on for 0.8 minutes, and the pump will run for a total of 4 minutes. It will run 5 times for a total of 4 minutes. Now with the CSV system, it will go on just once. It will stay on for the total of 20 minutes. And how can this be? Because the pump is fast, but the CSV valve will stifle the pump. It will force the pump. It will put back pressure on the pump, so the pump will only be able to pump at a slow rate, and the pump will stay on for the full 20 minutes of the shower, never go on. I mean, the good thing is that you will get constant pressure of 40 pounds during the total length of your shower. But when we look at this, we'll see that the number of cycles for the standard system is 5, and for the CSV it's 1, and you are getting constant pressure, so that's the good thing about this. But the runtime of the pump for the standard system is 4 minutes, and for the CSV it's 20 minutes. So it uses 5 times more electricity. Now the CSV man disputes this case. He says it doesn't use 5 times as much electricity, and he presents a case. And his case is wrong. It's just completely false. And later I will debunk the CSV man's argument. There's one other thing I want to say about this scenario, and that is this, that the CSV man says that the CSV is good in this situation because it will only cycle once, where the standard system will cycle 5 times. And cycling 5 times puts 5 times as much stress on the pump as cycling just once. But the other thing to look at is that the pump is running 5 times as long. With the CSV, the pump is running 5 times as long as it is with the standard system. So is it clear that running 5 times for a short period of time is more stress than running once for 5 times longer? I don't think that's clear. And when they talk about a pump's life, they talk about the total amount of time that the pump is on, usually the duty cycle. They don't usually talk about how many times the pump goes on and off. So I think you'd have to do some kind of study. I actually looked for this on the internet and I came up empty. But it's an assumption by the CSV man that the main thing that breaks a pump is the number of cycles. And I'm sure cycling is not good for the pump, but you also have to consider the total amount of time that the pump stays on. That is also a wear on the pump. And the CSV man does not consider that. Okay, now we're going to look at scenario 3. And this is using the water for a long period of time with a fast flow rate, but with a flow rate that's still somewhat less than the maximum flow rate of the pump. So we're going to assume a water sprinkler used for 2 hours, 120 minutes, and the flow rate is 10 gallons per minute, 1,200 gallons used. And remember, the flow rate of the pump is 12 gallons per minute, so the flow rate of the sprinkler is slightly less than the pump. Okay, so again, the math here, I'm not going to go over all the math, and please feel free to check my math and let me know if there's anything wrong with my math. But we will jump, and actually this math is actually in favor of the CSV system. It's the only situation. So let's look at the recap. For the standard system, it will cycle 25 times. For the CSV system, only once. For the standard system, the runtime will be 100 minutes, and for the CSV, it will go on the whole time 120 minutes. So finally, in this situation, in this particular very specialized situation, I will admit that the CSV is saving you money and doing a good thing, because it's reducing the number of cycles from 25 to 1, and It only has a little bit of more runtime. And in fact, it may use the same amount of electricity or even less because there's a little bit of a surge each time you start the pump. So I'm going to admit that in this case, the CSV valve is good. But remember, this is a very specialized situation where you're running it for a long time and you're running it close to the full capacity of the pump, but not the full capacity of the pump. Okay, in scenario 4, we have long water usage using the full maximum capacity of the pump. So an example of this is if you were filling a swimming pool. And the swimming pool, if it was 20 feet long and 10 feet wide and 4 feet deep, there would be 800 cubic feet of water, which translates to about 6,000 gallons of water. And if you're using the full capacity of the pump, in other words, you have a big hose, you're going to the pump, and the pump is basically just going directly into the pool, it's pumping at 12 gallons per minute, which is the full rate of the pump, and it will take 6,000 divided by 12 equals 500 minutes equals 8.3 hours to fill the pool. So now let's look at the math here. Okay, so what happens with a standard system? With a standard system, the pump actually never goes on. I mean, never goes off, sorry. With a standard system, the pump is on the whole time. This is because the all the water is going into the pool, and none of the the pool is drawing all the water, so none of the water is going back into the pressure tank, and the pressure tank is never filling up, so the pressure never achieves the 50 pounds cutoff, and the pump will run for the whole 2 hours. And with the CSV system, it's exactly the same. So in this situation where you're using the full capacity of the pump, the standard system and the CSV system behave exactly the same. And I want to point out that in this situation, the CSV man is doing a bold-faced lie. He says that when you're using the full capacity of the pump, that the system will still cycle. He says even if you turn on every faucet in your house, that the standard system will still cycle. And he says that in one of his videos, and it's a lie. It's a complete lie. If you're using a lot of water and you're exceeding the capacity of the pump, the pump will never go off, and the two systems are equivalent. So let's revisit scenario 2, which is a long shower at a low flow rate. And what I said is that it uses 5 times more electricity because it's on for 20 minutes with the CSV rather than 4 minutes with the regular standard system. But the CSV man disputes this case, and he disputes it because he says when the pump is restricted, when the flow is decreased, that the electricity rate goes down, the pump uses less power. And in this video here, which I've mentioned before, where he's promoting the CSV man says when you restrict the flow of a pump, the power usage goes down. And while he admits that some pumps are better than others, he says that the pump in this simulation uses 50% less power when severely restricted. So what does he mean, this simulation? You can put any numbers you want in a simulation. That's what a simulation is. Does it reflect a real-world pump, or does it not reflect a real-world pump? He also admits that this is counterintuitive. And yes, it is. So let me talk about that for a second. Counterintuitive? Yes, it is counterintuitive. Why should a restricted motor use less amps? So I decided to do a quick test with my old broken down fan and an amp meter that I have. As you can see, restricting the motor caused the power usage to go up slightly, not down. But okay, I admit an old fan is not the same as a modern pump. So let's go on and assume he is right for now, although later I'm going to question him again, as you'll see. Okay, so let's revisit scenario 2 recap again, and let's assume the CSV man is right and that it does use 50% electricity in the restricted state. Well, if we look at this example where originally I said it uses 5 times more electricity. Even if he's correct and the pump uses half the amount of electricity when it's running 5 times as long. So even if he's right, which I'm going to prove later that he's not right, but even if he was right, it would still use, in this scenario here, 2.5 times more electricity. So let's revisit his claim of 50% power reduction. When he talks about this simulation, when he's in the simulation, he says the 2 horsepower pump in this simulation. Oh, which pump is that? Does he name it? Does that pump exist? Well, I guess he tried to solve that problem. Maybe people said that to him, and he said, okay, I'm going to prove it. And so here's another video that he has on YouTube. And in this video, he says he will prove that pumps really do have a 50, in this case, he's showing that it has a 55% reduction in power when you restrict the pump, when you restrict the flow of the pump. So in this video, he will try to prove his case by showing you a real power curve graph from a real pump manufacturer, and he claims the pump as an example has a 55% reduction of power. So let's look at the flow rate that he shows in his video, at the flow graph, the power graph. And so here's the power graph, and I'm going to explain this a little bit. What this is showing is that when there's zero pump resistance, in other words, it's like the pump is just pumping, there's no pipes, no resistance, it's just pumping into the air, there's no resistance. The pump is capable of pumping 320 gallons per minute, okay? 320 gallons per minute at zero back pressure. Now then he's showing as the flow rate goes down, and the flow rate will go down because there's back pressure, there's pressure in the system, and so that causes it's like if you imagine it's pumping the water uphill, that the water pushing back is like the resistance, the back pressure, and sometimes they call that the head height in feet. It's like pumping so many feet of water up a hill, and you can see as the flow rate goes down, okay, as the flow rate goes, as the pressure goes up, as the back pressure goes up, the flow rate goes down, and eventually the pressure is so high in the system that the flow rate becomes zero. And here he's showing the horsepower. So he's showing that when you have the full flow rate, the horsepower is 24 horsepower. And when he gets down to the end where there's zero flow, it's only a little over 13 horsepower. Now the first thing I want to say about this is that he claimed a 55% reduction. This isn't a 55% reduction, it's a 45% reduction. So what he's saying is that in this case, the pump is using 55% of the power that it would if it was with no flow restriction. So it's using 55% of the power, so it's only a 45% reduction. So if you go back to his previous video, he's saying a 55 reduction in power. Well, that's a lie, even according to the slide he's showing. Even according to the slide he's showing, which is this one, it's only a 45% reduction. Okay, but 45% is still good. Now I want you to look at the pump he chose. 24 horsepower, flow rate of 320 gallons per minute. This is a huge industrial pump. This isn't the kind of pump that you have in your house. Why did he choose this example? Well, I'm going to guess, I can't know this for a fact, but I'm going to guess that he chose this example because he couldn't find a good example in a normal house for a residential system. Probably he had to go to a very expensive, sophisticated, commercial, industrial pump to get this kind of power reduction. It's probably a very sophisticated pump. And so he used this as an example, and this is a ridiculous pump to show in his example because nobody buys a pump with 24 horsepower and a flow rate of 320 gallons. I mean, the 3/4 horsepower pump that I spec'd out only has a flow rate of 12 gallons per minute. Okay, so he's totally misleading in this situation. So what I decided is, what about a normal pump? And I have a pump. This is my pump. It's a cheap pump. It's only 1/2 horsepower. It's cheap. I got it from China, and it runs my system. It's been running it for 4 years without any problem. And I decided that I'm going to do the test myself because I have an amp meter and I can test it and see if there's any truth to this reduction in power as the flow rate is decreased. So I will show you this video that I took now. Okay, here's my initial setup. In the top middle you can see the pressure gauge, but you can't see it very well. It's out of focus. So I superimposed a dial, but even that's not very good, but at least you can read it if you look carefully. On the left is a chart superimposed which shows which converts amp readings to watts and horsepower because the voltage is 220 and amps times volts equals watts. And then you can see the meter, the amp meter, and that will be taking the measurements in real time. Okay, let's get going. I will turn on the pump. Okay, stop right there, as Meatloaf would say. If you look at the meter gauge, the amperage gauge, you can see that the amperage is 1.98 amps. In a split second it will go back down. This is because when you first turn on a motor, there's a surge. But as you can see, the surge is quite small and only lasts for less than a second. And so it's kind of a myth that when you turn on a motor, it uses up a huge amount of electricity like some people will claim. In actuality, it's only a very small surge that lasts for a very small amount of time. Okay, let's continue. Okay, the initial pressure in the tank is only about 5 pounds of pressure, and as you can see, it started out at about 1.5 amps, and it's slowly going up as the pressure is going up. Now this is kind of boring, so I'll skip a little bit. Okay, you can now see that the pressure is around 30 psi, climbing towards its final destination of about 45 psi. And as you can see, the amperage is continuing to climb, and it will finally cut off at around 2 amps, whereas it started at 1.5 amps. So as you can see, as the pressure goes up and the flow is restricted, that the amperage actually goes up. The power consumption goes up, not down, as the CSV man claimed, which I think he knew that, and I think it's a bold-faced lie is what it was. Okay, so in the last part of this video, I'm gonna kind of summarize my thoughts and things that I think are wrong with his information and things like that. So let me first start with this. This Waterworld ad, which has a bold-faced lie in it. And it says that there are still disbelievers who can't fathom the simplicity of a mechanical valve that can deliver constant water pressure with equal efficiency from small flows to large flows, basically. And that's a bold-faced lie. It doesn't deliver equal efficiency under all situations. In many situations, the efficiency is very badly compromised. Okay, let's go on to bold-faced lie number 2. In one of his promotional videos, he says, with a regular system, even if you open up all the taps to the house, your pump will keep cycling. And that's not true. With a normal pump that's sized right, if you open up all the taps to your house, the water will be used so fast that the pump will not supply enough water to make the pressure go up and fill the water tank, so that the water tank will never fill up completely, and the system will never go off. So it will not keep on cycling all the time if you're using a lot of water. Okay, that's lie number 2. Let's go on to lie number 3. As flow is restricted, power consumption goes down, so you don't lose efficiency. That's basically a lie, because he's picking very particular pumps to show that the efficiency is better when the flow rate goes down, and in most pumps that's not true at all. And in fact, in a lot of pumps, it becomes less efficient as the flow rate goes down. And even if the flow rate does go down, even if the power rate does go down as much as he says it does, even so, you still lose efficiency and lose money in extra electrical costs. So basically that's a complete lie too. Here are some misleading statements. A CSV delivers constant pressure. Okay, it does in a long run. It delivers constant pressure. But in the short run, it delivers anything but constant pressure, as the pressure will first surge down and then surge up before it stabilizes. And another misleading statement is that CSVs reduce the number of pump cycles. Well, it's not clear at all that it reduces the number of pump cycles. In some scenarios, it may if you're using the water for long periods of time. But in a normal household where you're always doing things like washing your hands or flushing the toilet, I'll bet anything that the number of cycles actually goes up. For the average person, the number of cycles is going to go way up when you use a CSV valve. Here are some more bad things about a CSV valve. As I mentioned, wild pressure fluctuations when the water is first turned on. This is because it's a very small pump, a very small tank that will first empty quickly and then has to fill it. Then the pump will come on and it will fill up quickly to the halfway point when finally the CSV valve will steady the pressure. But before it steadies the pressure, there'll be a wild fluctuation in pressure. And another thing about the CSV system is if you get a powerful pump, you will be punished badly. Okay, so if you get a pump that's more powerful than you need with a regular system, maybe you'll waste some money because you bought a more powerful pump than you need and that costs money, but otherwise it won't really hurt you because what will happen is it will just fill the tank quicker and go off quicker. So it won't really hurt you that you bought a more powerful pump. But if you have a CSV system and you buy a more powerful pump, it will hurt you badly because the CSV system will limit the pump, will hold back the pump and not let the pump pump as much as it wants to. It will restrict the flow to a very small level and result in a very bad efficiency. So the bigger your pump, the more powerful your pump, the worse efficiency you will get. And in fact, if you really want a CSV valve system, you're probably better off with a small motor. Now, sometimes he says that he has said that if you get a big tank with a CSV, it will solve some of these problems. Well, not really. If you get a big tank with a CSV, it will solve the problem of the water going on and off every time you use it for short runs like washing your hands. But for most cases, if you have a very big tank, it will behave like a regular system, unless you have a very long run like a sprinkler system or something. But the other thing is, if you have a big tank and when it comes time to refill the tank, the CSV valve is going to restrict it to 1 gallon per minute. So it's going to refill the tank at a very slow rate. So as you can see, there's a lot of bad things about this CSV system. But the CSV man would have you believe that there's no reason whatsoever to ever not get a CSV valve. So let's be fair. Is there any case when you would want to buy a CSV valve? Well, I guess yes. If you don't care about the extra electrical cost, if you don't care about the longer runtime of the pump, if you don't care about the pump going on every single time you wash your hands, if you don't care about the extra on-off cycles of the pump, if you don't care about a sudden pressure drop followed by a sudden pressure surge, followed by steady pressure every time you use water, if you don't care about any of those things, but your overriding concern is to have steady pressure when taking a shower or running a water sprinkler without the pump cycling during those long runs, if that's your overriding concern, well, in that case, I guess a CS valve is for you. Hi, so I thought I'd give some final personal thoughts on this video. I put a lot of time and thought into this video. And one of the reasons I made this video is because I took it personally. I put a comment on one of his sites, CSV Man's videos, and as I showed in my presentation, he answered me that I just didn't know what I was talking about. I didn't know the principle. And I took that personally because I'm an engineer and I take pride in understanding these kind of things. And it kind of bothered me that he's trying to sell this product that's really not a very good product for most people in most situations. But he has a company and he's trying to make a life and he's trying to make a living. And so he floods the market with disinformation, misinformation, disinformation, and pretty much lies, trying to sell this product so he and his family can make a living. And I don't really blame him. More power to him. Everybody has the right to try to make a living. But on the other hand, he's hurting people that are buying this product thinking it's a good product. He's telling them that it's a perfect product with no downside and that there's no reason whatsoever not to get a CSV. And people are spending their money and losing money on electricity and things like that. And there's nobody to sort of tell the truth because they overwhelm everybody with disinformation. So I took it upon myself to make this video to set the situation straight. And if CSV Man wants to comment, and it's a reasonable comment, I'll leave it on my video. I'll give him a chance to answer. But the truth is, I know that everything I said is right, and he can't really refute anything. He could just get annoyed and say things like, "You just don't understand. You just don't understand." But I guarantee he can't really refute any of the things I said because I understand the principle, and the things I said are really accurate in this video. So I hope I stop some people from buying this product that otherwise would have bought this product because all the disinformation. And if I hurt this company because some people don't buy the product, well, I understand that they're not happy about that, but there's the flip side where a lot of people will be saved the hassle and the expense of buying a product that they think is good that's not really good. So anyways, I made the video. I put a lot of time and effort into it. I hope it helps some people. Thank you very much. Bye.